Hey, we should be live now. Hey everyone.
Hi everyone.
Just had an entertaining time trying to fix resolution issues. So
It's also
uh,
not live for me.
no, it I think it takes a bit to catch up. Yeah, there we go.
Thought
We're going
we're
live
on
now.
low latency.
Oh, normal now.
Ah, okay.
Just had yeah, we're sweet. We're live. Quality as usual. Like our starts, they're just so definitive. You know, everyone's like they're here. They're not like, is it working yet?
Is it working yet?
Which is how we roll. Although it said we had 5 people waiting, and
And now
now
there's a one.
yeah, uh,
Those 4
geez,
minutes, that's all it takes.
no 3.
Four,
Didn't know time travel worked faster in Queensland, Jake.
it says it's 7:04.
Let's anyway. How have you been?
Yeah, not too bad.
That's good.
Melting, but not too bad.
Yeah, is it hot up in Queensland?
Yeah, it's hot up in Queensland.
Man, that's no fun. It's rainy and cold down here, so
That's all right.
time travel. Anyway, so what are we going to do today, Jake? Well, I'm running things this week, so we could be doing anything. Look out.
Uh-oh.
Yeah.
I have no control.
So last week, while everyone can look at my Carly login screen with the time. So last week we looked at using reversing. So we used Ghidra to decompile a little program Jake had written. We looked around and changed a value, and effectively created a patch that patched out something we wanted to bypass or change a value. So anyway, we could execute some logic we wanted to execute. So this week, we're kind of doing something similar, which is using a debugger to achieve a similar goal. So I've written this little app. Doesn't really do much. It's just as much of a kind of toy as Jake's one was. But
Yep.
all it does, we've got a main function here. If you know anything about C, main is the special name given to the actual function it's going to run. Plenty of languages have this concept. Even behind the scenes, Python does, even though it's not obvious. So what we're doing is we're generating a random number. So we're initiating the random number generator in C with which is srand or secure random, I think, just with the value of the current time. And then what we're doing is we're throwing that into an int called check, setting up an int for some input. We're telling the user to input a number, not doing any sanity checking. So if you put in an A, it's going to break. Or maybe it won't. Maybe it'll read an A as its numerical character value. I haven't checked. But here's where the fun bit is. You effectively have to guess a random number to get the thing to run properly. So you get this, you got it right, boy. And if you get it wrong, you get this, get it together, kiddo. So what we want to do is see this and not this. So if I compile it, I have been calling it thing, but I'm just going to call this guess. I'm so creative with names. So if I run guess, which I'm going to have to do like this, please enter the right number. Wrong. Let me try that again. Please enter the right number. 7. Nope. Let me try again. Nope. I got it wrong. I don't know, Jake. How am I going to figure this out?
I don't know. I think we gotta.
I could use Ghidra to sit there and reverse this thing, or I could use a debugger. So on Carly, I know Jake last week was using Parrot, which is another kind of security-focused Linux distribution. I'm still on Carly. But there is a debugger called EDB.
Yeah, they both have it pre-installed.
Yeah, so EDB is a visual front end for GDB. I mean, I could actually quickly demonstrate GDB guess, and I think you just go run. But because there's no debugging symbols, it's not really going to tell me anything. But GDB does have a ton of other information about the app that you can use. There's a ton of commands for it. But why sit there learning them all when you can just use EDB, which is a visual front end for GDB. So that's fine. I don't have a session file. All good. So this is our app. Well, the kind of it's analyzed it. So this is the assembly. This is the machine kind of instructions that are running. You may also notice, if you have a look, and I'm just going to double check the YouTube video that it looks clear enough. Yes, it does.
I can read it, yeah.
Sweet. So if I go back to VMware. So we've actually started an ld.so, which is, I'm pretty sure, like the linker, ld.so. I actually, last night, had planned to Google this so I could give you a quick answer, but...
I'm pretty, yeah. It's kind of like a library, like the lib.so that
it's
we
the
have.
So it's the dynamic linker. So effectively, I rely potentially on a bunch of libraries that aren't statically compiled into my app. So
yeah.
quick rundown on how stuff's built. Also, I'll talk about the security implications of all of this in a bit. Don't worry, that is coming. But
it's similar to the libc.so hijacking stuff we've done in the past.
Also, that's all relevant. So dynamic linking or runtime linking is where your app has a bunch of dependencies, and you could either statically include those in your executable, potentially making it very big, but fairly portable on systems that support your binary type. Or you can dynamically link, which means rather than like compiling, and let's say you were using a library to make web requests. I don't know if there is one in C, but let's just pretend there is an SO that does. And you didn't want to include all of that code in your executable. You might only use 2 functions from it. So as long as someone's got that library installed, that runtime at startup, LD's kind of included with as a dependency in every app, and it'll go, right, you need these libraries, I'll go and grab those and load them into RAM so that you can call them. So that's all this is doing. This isn't actually that important. It was just interesting that it starts you there. EDB quite conveniently puts a breakpoint at the main function of your app. So this kind of memory address here. So it drops this in. So here's kind of the assembly for the binary we're in, whether it's like guess, which is the name of the binary I just compiled, or it could be the SO file that you jump out into. So if you don't jump over all of these calls, and a call in assembly is basically run the code at this address, and it'll jump you into that address, which they're all going to be another DLLs, unless I went and wrote extra functions, in which case you could get a call into the same binary. Over here, we've got all our registers. So registers are, on a modern CPU, they're all kind of virtual. So my executable has access to all of these registers, but under the hood, the CPU probably has multiple physical registers that it logically maps through per app. But a register is just it's not that big, but it's kind of you can shuffle data in and out, or you can shuffle addresses in and out. So some that are interesting. So RAX, RCX, and RDX, I think even RBX, are all data registers. So they could hold addresses or values. RSP is the stack pointer, so the top of the stack that you're on. If you remember back to uni, if you've ever done kind of IT stuff at uni, the stack is the place that your app kind of does a lot of its work on, so stuff gets chucked on it and pulled off it. It kind of moves up and down. It's kind of like, for first in, first out. So if you put something on the top of the stack to get it back, so to get something underneath it, or we do show that you can go through and pull stuff deeper down from the stack, but effectively you just pop off the last thing on the stack. So normally that's how your program's execution's controlled and stuff like that, and local variables and stuff. The base pointer is the base of the current stack frame, so the particular context of code you're in right now. So here, it's all this kind of red stuff as the current stack frame. So if we have a look, RSP is 738, which is here, and the base pointer is 1F0, which is actually all the way back up here. But
somewhere up there, yeah.
It's about to go and initialize the stack frame. So that's what all this stuff is. So, yeah, copies the current stack pointer into the base pointer. Now, if you have a look, the stack pointer and base pointer are not the same yet because I need to go to the next instruction. It pushes the current base pointer onto the stack so that we don't lose the value that it had. Otherwise, bad things would happen. Then now the stack pointer and base pointer are the same. Then we're taking the value, hexadecimal value of 10 off the stack pointer. And now the stack pointer and base pointer are 10 apart. And if we have a look at here, we've got the base pointer is down here at 30, and the stack pointer is here, and here is a bunch of blank, zeroed out memory, which is where the locals will go. Then my bit of code, if we go back over here just to keep things compared, so many windows. Where's the little here we are, EDB output. We want this as well. So I will caveat this with I'm no expert in low level machine code, so there may be little bits and pieces I'm getting wrong. So again, we've got a call. So this call is probably either to time zero srand to initialize. I think it's to time zero because that'll be logically the first function that'll need to be called because that'll output into srand. So if I go here and then I'm going to go step over, otherwise we go for a little adventure. Every time I've accidentally stepped into, it's like takes forever, and then you try and go step out of it and like something breaks. So this is the easiest way to do it. So it's just moving some more values around. So EDI, I think, is another data register. So it says EDI and EAX here. One thing to note, in 32-bit land, the registers start with an E, and 64-bit land, they start with an R. Because I'm running on a 64-bit operating system, but I've compiled a 32-bit executable, this is talking about EDI and EAX, but over here I've actually got all the registers. And here it does, in some cases, refer to the R's as well, so I'm not exact. Maybe it's all how this thing just reads the base, whatever, the kind of application code out to assembly. It's just moving some more values around. So this EAX is probably the return value from this. So it's just moving that to EDI. It'll call a couple more functions. We'll step over those. And now we've got this. So this, so the output from our rand function is just here. So now what we're doing is EAX is the output, probably output from that random function, and we're moving that into the stack, 4 bytes offset. Remember, we've got 10 bytes of space on the stack here and here, and so we're moving that into at minus 4 bytes this value. What I'll do is I won't worry about trying to abuse the code flow. We can just kind of demo it and then go through it again. So that gets loaded just here. You can see this 147297CB, 147297CB is now loaded into the stack. So let's say 1, 2, 3, 4. Yeah, it's a 4-byte value. Yeah, so that's why it's minus 4. It's given it enough space on the stack. So which a 4-byte value, that's just a standard int, I think. Now, LEA is load effective address. So it's getting the address for where this text is stored. Please enter the right number. I'm just going to step over. We don't need to go through this call is to the C printf function. Then we're just loading another effective address for bits and pieces.
And those aren't nearby because they're loaded from, like you said, the main C libraries. They're not part of your app necessarily. Unless
I wrote my own print function.
Yes.
Yeah. So that jumps you out into like libc, and then you go on for days because it does a lot. This is the thing, right? I'll put it like this. Assembly is like Lego. So if you had nothing but Lego bricks, they're really easy to put together. But as soon as you want to, say, make a Star Destroyer with them, like, it gets complicated fast.
You have to put them in the very specific correct order to make it.
And that's what using assemblies like is. It's all of these very simple primitive operations that get really, really complicated fast because you've only got so many primitives that you have to build complicated things out of. That's just moving some more. RSI, that's the stack. Jeez. Quick, Jacob, do research. I've forgotten. Anyway.
So that's the stack, the RSI, is that the source index? So that's like
728. It's currently sitting at 728. So whatever was in RAX gets loaded into RSI. Anyway, it's just doing some more stuff. It's probably loading in some input. So yeah, it might be loading in some input to something else. Anyway, we'll just step over this call, and at some point, there we go. We have to give it input. So I'll give it a 5. And if I step down, so the output from our scanf has been put in the stack at -8 bytes. So we can see a 5's shown up here. And what's going to happen is now there's a 5 in RAX. So it needs to be in the register, I think, because it needs to then use it in this compare. So, yes, that's right. So the square brackets around these things. So if you know anything about C and you know about dereferencing, so with C you've got pointers, which is a memory address where some value is located. And then you've got, like, when you dereference a pointer, you've got the actual value that's at that address. So the square brackets indicate get the actual value that's at this address in memory, not the value of the address. So this is comparing the value in this register. So the way it works is registers, you'll get whatever values in the register, whether it's a memory address or no, because they're just numerical values at the end of the day, or binary. This thing here, though, we'd be comparing it to the actual memory address of RBP unless we had the square brackets around it. So that's all that does, and this is a compare, so it's checking if these things are equal to each other. The very next thing it'll do is a jump if not equal. So what happens if these aren't the same? This thing will jump us to 1D0. Yeah. So it'll jump us to this one, which, as you can see, wrong, get it together, kiddo. Interesting thing to note, in addition to registers, there is a bunch of flags that exist in the CPU. I'm assuming they've got the same kind of logical construct, that this app sees only one set of the flags it needs, but the CPU has tons of copies of them. We've got the 0 flag, which is basically, so when an operation finishes, this flag can be set to 1, which indicates that there was a 0 as an output, or can be set to 0, which means there was a non-zero result. It gets confusing because it's a flag, so it's binary on or off, not 1 or 0, but it's shown as a 1 or 0. So what'll happen is we should jump, and we get this like load effective address thing again. It'll do a function call. It'll move 0 into EAX because it's finishing things up, but we got a wrong get it together kiddo down here. And leave just starts to clean everything up, I think. So that undoes a bunch of stuff, and then return, and that'll jump us back to libc to probably clean us back up. So I haven't really looked past where we finished up, but that kind of shows us that. So I wonder if there's a way to like debug restart. Oh, you can just restart. Cool.
Nice.
So I don't have to like close it and open it again. So what we're interested in doing is bypassing this bit of logic. Now, last week we talked about things you might use this for. The challenge with debugging as opposed to reversing is like for malware. A lot of malware has anti-debugging kind of logic built in. So one of the easiest ones is to check timing, and if things are taking too long, like so, you know, you get the current time every time you run certain operations, and if all of a sudden it's minutes between things that should have taken microseconds, it means someone's running a debugger and probably taking their sweet time. Whereas reversing, you don't have that problem, but reversing, you have to desk check the application flow yourself. You can't watch it in real time. Some of the other things you can be using a debugger for is if you want to see if there's any potential vulnerabilities in an app, looking at it in runtime. So like what we're doing here, can you bypass certain checks? Naturally, there are nefarious uses for this, so again, not recommending you do that, and modern apps tend to have enough protections to prevent this stuff too. But, you know, this is old school, like, you know, your cracking groups in the 80s and 90s probably were doing some of this sort of stuff, so where you'd have a check for something in a debugger, you'd run it through, try changing values to get it to bypass a particular check. Then you might go back into your reversing tool, find the location, change some instructions so that a check's bypassed. So if we hit play, we should stop again at our main function where the RAX pointer is currently pointing to. Right. So we're going to set up some breakpoints. So we want to set up a breakpoint at this point here again, where we know we've got our value, and we want to set a breakpoint before this compare runs so that we can change the value of EAX before the compares run. So what we're going to do now is just hit play, and that'll take us to this first jump point. So if I go and grab the value of EAX and just dump it there. So that was from where I was doing it earlier. So that's our random value. Actually, if we have a look at it again, 177. Well, actually, 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's like 1.7 billion. Is the value? There's a good chance I would never have guessed that. So,
just a small chance.
Yeah. So I'll close that. Right, we've got that recorded. Now we'll just hit play again. It's expecting me to enter the right number. So if I hit 5, right. So EAX is currently 5. It needs to be this value. This is really easy. Done. And now, if I hit play, I should get. You got it right. So all we did there was literally change the value, in a register to bypass a particular check at runtime. So this is no different to like, it's really just a kind of like a form of injection attack, or, debugging's the same, and no matter the language, I mean, JavaScript, Python, whatever, this is just a lot lower level than all of that. Yes, I think I've done this before. Like there was some challenges with JavaScript where you just used a web browser debugger to change values to get the right outcome. Right here. And it also goes to show this is why client-side controls aren't effective. So if you think about like, there was one pen test I was on, and there was a front-end app that talked to a database. The front-end app had a field vulnerable to SQL injection, but it only allowed, I think, a couple of characters, like front-end display logic. It was written in .NET, so we'd need to use a .NET debugger instead of like this one. And we didn't really have time to sit there and go through it. But in theory, we could have gone through it and either altered the app in runtime, or if we'd reversed it, just recompiled it, so that limitation on the characters wasn't in place in the front end, and then bam, we could just write full SQL queries, or we could have just altered the value in memory to be a longer string before it was sent. So you can do all the same sort of stuff you would do with this is effectively like a intercepting proxy, or burp for binaries, if you think about it like that, if you've used burp before for web stuff. So it lets you kind of interfere. So if I go restart, there is one other way we can abuse this. So
I was going to ask if we were going to go through that. We've got some time.
Yeah, I know. This might not be the longest stream. Nice, punchy, quick one. I'm still recovering. I was not well last week. So, radio. So remember when I talked about that 0 base flag? See here, it's set to the 0 flag is set to a 1. There's also the carry flag. So I think that happens when you've done an operation, like you've added 2 numbers together. So an int is a 4-byte value. You've tried to add 2 numbers together that overflow a register. The carry operator can get set, and then you can use that to do more processing to add bigger and bigger numbers together. So I'm only inferring this, but I'm guessing in assembly, to add massive numbers together, you've effectively got a loop. And addition and binary is pretty straightforward, but you just have to keep looping through the value and storing everything in memory and chunking it through to add massive numbers together. The carry bit would indicate I've overflowed, and now you need to do some additional processing to get the actual value. And the 0 flag, I think, really is just the return code, or the kind of for evaluation operations. So in this case, to change this one, all we need to do is go to our jump of not equal. We don't need to check anything out. This is actually the easier way to do it than the first way I did this. Because last night when I was trying to figure this out, I kept trying to pull the value out of this little stack kind of indicator area here, and I kept getting it wrong. Before I realized you could just catch it up there. And then I was like, wait a second, I'm sure you can just play around with what this uses to evaluate if it should jump or not. So let's just run this through, enter the right number. 5. 5 is clearly not the right number, and our 0 flag is now set to false. So if I toggle this back to a 1, the jump of not equal is going to go, yeah, you got it right. So that's...
Yeah, so the jump of not equal is looking at that character and going, did the compare say that it was a match or not?
This is so the jumps are kind of your primitive for how you would do trues and false, sort of, or ifs, I should say. So, you would go if, so you do a compare operation, and if they're equal, you go jump to this memory location, run this code, and then there'd be a jump at the end of that to jump you back to some other place where you could control. So luckily for us, various compilers that we use do all this stuff for us. So we don't actually have to worry about thinking like this, because what assembly shows you is that all code is spaghetti code. Like, you might write the most neatest, high levelist, object orientedest, functional programmingest bit of code, and it'll end up just being this massive bunch of jump all over the place spaghetti.
Yeah. The compiler still boils it all down to that.
Yeah. So there's a bunch of compiler optimizations and stuff that you can see. Well, actually, I'm not that worded up on compilers again. This is the
good example that I sort of go back to is a couple of years ago now, I think. Cloudflare had a vulnerability or issue where the compiler that they were using was misinterpreting a greater than or equal to or something like that. And down at the assembly level, it was treating it as an equal to. So basically, this whole chunk of code never got executed because the code was expecting it to always be greater than, so that it would enter this code chunk. But the compiler sort of changed it around and said, no, I want an equals to. And so yeah, there was an issue with their code never running correctly because of the compiler converting the code into the wrong assembly. Yeah,
trying to optimize. So
optimizing it down.
one of the other things to note with this stack is we've got this, kind of construct here where we are going to clear out. So if we go through and they set up the stack so that we've got the pointers all set properly, and then we zero a bunch of stuff out. So here is where the locals are for our app, all these zeros. Depending on the context of your app, if I went and created tons more variables with tons more data in them, I'm going to guess it's going to try and allocate more room here. In fact, we can probably test that. We've got enough time.
Yeah.
Int thing equals that's right, you gotta do these bad boys. Int fun equals it doesn't look it starting with a zero.
Yeah.
So we should then just be able to, so to ensure these get used, print, because again, compiler optimization can be unpredictable, and it could actually remove these empty variables with, well, not empty, these unused variables. So we force it to use them by sticking them in a printf. Let's see. Yes, thanks. I do too much Python. I will clarify, one of the advantages of working in security is you get to learn a bit about a lot. One of the challenges is this is a field that this particular area, the low level stuff, is something I'm starting to get into, and it's really interesting. But it does mean you kind of end up in the category of jack of all trades, king of none. So that, which I don't mind, I enjoy. But it does mean sometimes you can be wrong. Oops. It does not I've created a long.
So it's higher than the int32.
Don't worry, we can. Int32, so 32 bits or 4 bytes, which we were seeing earlier. So now it should compile, and now. Where was I running? EDB, that's all right. Okay, so EDB output. Now if I just go to the start of the main function. It's still only
maybe it still only needs 10 bytes.
Maybe. Well, actually, I think it might be 10 memory addresses that it sets aside, and this just shows you. 10 memory addresses is still 10 bytes, though. So anyway, if we jump through, so there we are, setting everything up. Call all that stuff. We move our thing, and then it sets the values we just went and created. So these D words are double words. No, words. Sorry, yeah. A word's 2 bytes or 1 byte, 2 bytes. So now this is looking a little bit more cluttered. And here, if I keep going through. At some point it should stop because it wants me to. There we go. Oh no, it's not. Okay, stop there. So there we go. We've got our numbers chucked in the print. We do our 5. Step forward because that jumped it in at. Yeah, maybe there is enough room to shove it all in there. Or it's getting rid of it because it doesn't need it anymore. Let me see. It could have done that as well.
Does C have garbage collection
No.
I didn't think it did, yeah.
Oh, well, the compiler will sort out some stuff, but when you're, allocating memory for large objects. So here we're only using the stack. So we're letting C figure out the stack. If you use malloc, I think that's where it'll go and actually allocate stuff in memory. And if you forget to demalloc, it'll just stay there.
Yeah.
So one of the other things with the stack, though, is the reason why we always initialize. So apparently, you can just go and use these. So if we created another function and just used these variables without initializing them, it'll just go and use existing stuff on the stack. And so that's how you can end up pulling old values off the stack, is if you don't initialize your variables properly in assembly or C. Assembly doesn't really have variables. Then what'll happen is the stack will have some old stuff on it. You will then, in that memory location, you'll then go and do this stuff that's further up here to allocate a stack frame, wherever 55 was here. So, was that it? Or was it somewhere else? Here. So, here. So they're doing all this stuff here to allocate the stack frame. So, to set up the spot on the stack that we'll use. And there'll be previous values in it. And then you'll be using previous values. So, there's all these little things. I mean, the reality is compilers and modern languages handle all of that for us. We don't have to worry about it. But when you're a Cloudflare, so where this is still relevant is when you're running at the scale of a Cloudflare or probably a bunch of Amazon stuff or even Akamai, you're probably going and actually writing stuff all low level to get the performance you need. Whereas if you let, while Java and .NET are fairly performant at scale, it probably still is better to have someone who knows what they're doing write a bunch of low-level C to eke out the maximum amount of performance from your servers or app or whatever you're doing. And if someone gets something wrong or a compiler optimizes something wrong, then you end up spitting back the wrong bit of information. Good. That's kind of that.
Yeah.
This does mean, though, we reckon between the two of us, we've learnt enough that we might actually start looking at trying to create some more complicated reversing and debugging challenges.
Yeah, I'm interested to keep going down this path, at least a couple more streams. So I think next week we'll come up with something similar. Not exactly the same, but something, I don't know. We'll figure something out.
We'll try and
but
create
still along the lines of reversing and debugging and messing around at this low-level stuff.
Well, I might even go and do a bit of... I'm running off the top of like what I remember from university and what I've learned over the years. I might actually go and do a bit of research so I can properly describe all the bits where I've gone, I think it's this, but I'm not sure. Oh, good. Well, anyway, thanks for tuning in. A bit of a shorter one today, but...
It was to the point. Hope you learned something about...
I mean, you know what, it is
like debugging or assembly or something.
It is 8:40. It's almost bedtime for people.
It's close enough.
All good. Cheers, guys.
Thanks. See ya.